All right, now the only time that probability of multiple events could start to become a little bit tricky is when you add in conditional probabilities. But that's what you just have to think, is that conditional probabilities means that the second event simply stems from, or is because of, or is impacted by the first event. So that's why tree diagrams really help a ton here. All right, here's an example. There's a 7% chance a new car breaks down. If the car breaks down, there's a probability of 8% it is because of an electrical issue. If the car breaks down, there's a 26% chance it's because of an engine issue. So before I even read the questions here, one thing you kind of think about is the tree diagram. So the car breaks down, right? It either breaks down or it doesn't. Now right away, there's a 7% chance a new car breaks down. So we could say that's a 7% chance. The doesn't would be 93%, right? 7% chance it breaks down, 93% doesn't. Makes sense. Now, if it doesn't break down, then that's the end of it. It just doesn't break down. If it breaks down, then it says there could be an electrical issue or there could be an engine issue. So their chance that it's an electrical issue is 8%, so 0.08. And the chance that it breaks down because of an engine issue, so put engine here. Sorry, my handwriting is terrible, by the way, but you guys know that, is 26%. But again, that 26% is off of it breaking down in the first place. It's not like there's just a 26% overall chance that you have an engine issue. You have to break down first for it to be an engine issue. So that engine and the electric issues are stems from it breaking down. Now you might say, well, wait a minute, the 26 and the 8% don't add up. Well, there are other reasons a car could break down, right? So if we add up the 26 and the 8, that's 34%. So that means the remaining 66% could be that it broke down for some other reason. So we could even add that if we wanted to. So other, right? Just put other. The other reason why a car could break down is 0.66. So 8% chance it breaks down because of an electrical issue. If it breaks down, it's 26% chance it's an engine issue. And if it breaks down, there's a 66% chance it's, who knows, something else. Okay. So what is the probability a car breaks down? Well, first off, you understand there's two ways a car could break down. It breaks down because of an electrical issue, or it breaks down because of an engine issue, or it breaks down for some other issue. So we just got to follow those branches, right? So it'd be 0.07 because it's got to break down first, then 0.08 breaks down because, again, the 8% was because of the 7%. Or breaks down and then it's an engine issue. Again, the engine issue only stems from it breaking down, or it breaks down and it's something else, some other issue. Now, let me go back and teach you real quick how I got that 66. When the car breaks down, it has to be for a reason. There's 100% reason that, if you think about why'd your car break down? Well, there's got to be an answer. So 8% electrical, 26% engine. The leftover can't just be, well, it's got to be for some other reason. So again, those have to add up to 100% or 1 if you're using the decimals. So 0.08 and 0.26. That's 34%, so the remaining 66% has to be from the other. So again, what's probability car breaks down? 7%, 0.08, 0.07, 0.07, 0.6. I'm sorry, I went through that real fast. It breaks down and then electrical issue, or breaks down engine issue, or breaks down because of other. Now, when you're going to hate me for this, but I just want you to understand this. Watch what we're going to get when we do the math on this. 0.07 times 0.08. Or 0.07 times 0.26, or 0.07 times 0.66. Hopefully you're doing that math with me on your calculator, but the answer is 0.07. Some might be like, well, wait a minute, duh, right? Duh. If it broke down, that's 7%. It said that. There's 7% chance a car breaks down. Whether it's electrical, engine, or other, who cares? 7% chance it breaks down. So listen, I'm not trying to convolute this. I'm just trying to make sure you understand that you could just say, hey, I know there's a 7% chance my car breaks down, or you could walk through the scenarios, but you still get 7% chance when it's all said and done. All right, what is the probability a car breaks down because of an electrical issue? Now, this is very specific. This would be breaks down because of an electrical issue. This would be a very specific, it's got to break down first and then be because of an engine issue. 0.07 times 0.08. And that would be 0.0056. So again, very slim chance, very unlikely, about 0.5%, 0.56% that it breaks down because of an electrical issue. All right, what is the probability the car does not break down? Well, wait a minute. We already know that branch. That's just the opposite of it breaking down. That'd be the 0.93. It doesn't break down. Well, how did it not break down? What do you mean, how did it not break down? It just didn't break down. There's not a 3% chance it didn't break down. So again, pretty simple, but just try to walk through that so everybody understands that. Pretty cool. All right, another good problem where a tree diagram could help. A horse is entered into 2 races. The probability that the horse wins the first race is 30%. Okay, so kind of like make a little chart here. So first race, there's a 30% chance of a win, which unfortunately means there's a 70% chance of a loss. Okay, well, hey, it's the first race. If the horse wins the first race, so this is conditional. So let's draw a tree diagram. This is going to really help me. So first race, win or lose. 30% chance of the win, 70 for the loss. Okay, here we go. See, I got to follow the branch, right? Because it says if is conditional. If the horse wins the first race, okay, so now I'm on this top branch here. The probability the horse wins the second race is 45%. So if he wins the first, on the second race, he could also win or lose. And it says if he wins the first, 45% chance he wins the second, which would, again, you got to use a little bit of math in your head here or in your calculator. 45% chance he wins the second, 55% chance he loses. Good. Got to add up to 1. All right, if the horse loses the first race, that's the 0.7 branch, he could then win or lose the second. Now, if he loses the first, the probability he wins the second is 10%. 90% chance of a loss that second time. So again, the horses are like humans, right? They got thoughts, they got feelings. So if the horse wins the first race, 30% chance, but now he's feeling good. He's feeling pumped. I won that race. So now on the second race, he's actually a little bit more likely to win at 45%. But if you lose the first race, like a human, you're upset. That horse got a long face. He's sad. And now he's bummed. He's so upset that he's much less likely to win that second race. His winning probability drops to 10%. Again, how easy is this? All right. First question, what's the probability he wins 1 race? Okay, well, listen, I don't care. It just said wins 1 race. Didn't say the first or second, just wants to win 1 race. So this branch would make me happy. 1 race. Top branch, no, that's 2 wins. We don't want 2 wins. We want 1 win. And then this branch right here is also going to make me happy because it results in 1 win. The bottom branch is 2 losses. Well, I didn't ask for 2 losses. I want 1 win. So this would be win the first, 30%, then lose the second, 0.55. I just followed that branch. Or another scenario that results in a single win would be lose the first, then win the second. Both of those branches end with me winning 1 race. So 0.3 times 0.55 plus 0.7 times 0.10. So 0.235. So 0.235 is the probability of winning 1 of the races. Don't care which one. All right, next question is a little bit tricky. Given that the horse wins the second, what is the probability the horse wins the first? Okay. Conditional, given. Okay, here we go. Find the probability. What does it say? It says, what is the probability he wins the first race? Probability wins first race. Sorry, my writing's bad. On the condition, it's given that he wins the second. Okay. Now you might say, well, probability wins the first race. Oh, they told me that, 30%. No. You are told the horse won the second race. Yeah, we know that. That was the condition. Horse won the second race. Now we can say, okay, what was the probability he won the first race? Because if you win that second race, that happens right here and right here. That doesn't mean he won the first. He could have won the first or he could have lost the first. That's why we got to work a little bit differently here. So we're going to use our conditional formula. Denominator first. What is the probability he wins the second race? That goes in the denominator. The condition is your denominator. Okay, winning the second race. Well, there's 2 ways you could win the second race. There's a way where you win the second race. There's a way when you win the second race. So I got to put both of those together. So winning the second race could look like this. 0.30 times 0.450, 0.45. Or 0.7 times 0.10. Both of those scenarios end in winning the second race. And right now, the denominator only cares about winning the second race. 2 ways you can win that second race. Let me do the math on that real quick. 0.3 times 0.45 plus 0.7 times 0.1, and we get 0.205. So my denominator is 0.205. That's adding together the two branches that lead to winning the second race. All right, now on the numerator, we want to win the first and the second. Remember, the numerator is both, winning the first and the second. Only one branch is winning both. And that's kind of cool, actually. It's kind of highlighted there. It looks like terrible. But anyway, that would be 30% for the first and then 45% to win the second. So 0.3 times 0.45 is 0.135. 0.135. All right, so now we just got to divide 0.135 divided by 0.205, and we get 0.659. Rounding to a couple decimals there, 0.659. So if he wins the second race, there's a really good chance, almost a 66% chance that he did win the first race. Weird question, but again, really walking through that, understanding the branches and the conditional is awesome there. All right, another problem where tree diagram is going to be very beneficial. There is a test for a certain type of cancer that affects 1 out of 2,000 people. So it's a cancer where 1 out of 2,000 people get it. That does not mean exactly 1 out of every 2,000 people get it. That's in the long run. 1 out of 1. Let me actually get a decimal on that. 1 out of 2,000 is 0.0005. I'll write that down so you guys can see that. 0.0005. So very, very unlikely that you get this cancer in the long run. All right, if a person has the cancer, the test will show a positive result 98% of the time. So this is a test to try to detect that cancer. If the person has this cancer, it'll show a 98%. So this is where I start thinking, all right, well, let me make a tree diagram. All right, here is my person. They might actually have the cancer. The probability they have the cancer is 1 out of 2,000, or again, 0.0005. There's the probability that you fall in that branch. Very unlikely to be on that branch. And then the probability that you don't have cancer, well, that's just the opposite. That would be the 1,999 out of 2,000, right? 1,999 out of 2,000 would be 0.9995. Look at that. So again, 0.0005, that's the probability you have the cancer. Very unlikely. Probability that you don't have the cancer is very likely. All right, but now we have this test. And this is conditional because it said if. If they have cancer, so I'm on this top branch. If they have cancer, the probability that the test will show a positive result, again, like it should. Oh my God, you have the cancer. It should give you a positive result. But that does happen 98% of the time. Well, that means that we get these what are called false negatives. It's a negative, that's wrong. You actually have cancer. But again, that only happens 2% of the time. 98% chance that the test shows positive, 2% chance it shows a false negative. All right, what about that bottom branch here? Because it says if a person does not have the cancer, it will show a positive result 5% of the time. We call that a false positive. It says you have the cancer, but you really don't. That happens 5% of the time. Which should happen is you get a negative result. You don't have the cancer, it should be negative. That would happen 95% of the time. So anytime you know a probability, you actually know two probabilities. Because if you know there's 98% chance of a positive, you know there's 2% chance of a negative. It just kind of goes hand in hand. But again, these are conditional. It says if they have the cancer, positive is 98. Negative 0.02. If they don't have the cancer, a positive 5%, that's a false positive. 0.95 would be the true negative, I guess you could say. All right, here's the question. What is the probability that a person takes the test and gets a positive result? Well, there's two branches that lead to positive. There's a branch that leads to positive. There's a branch that leads to positive. Just got to multiply them out to figure it out. So we could have the cancer, 0.0005, and then test positive. Or we could not have the cancer, 0.9995, and then test positive as well. So these false positives do happen. So again, take your time on multiplying this on your calculator, 0.0005 times 0.98 plus 0.9995 times 0.05. And we get 0.050465. I'm going to write all the decimals down just for fun. 0.050465. So, you could say roughly a 5% chance, very rough, a little bit more there, but roughly a 5% chance that a test comes back positive. Now, you might say, well, wait a minute. This is 5%. Well, actually, that's exactly 5%. This is a little bit over 5%. So again, most people don't have cancer. So that means that the probability of a positive result should be really close to 5% because most people don't have the cancer anyway. But there is a chance that you do get that positive result, if you actually have the cancer. But having the cancer is so rare. Somebody might say, but wait a minute, it says 98% chance of a positive result. Wouldn't a positive be more likely? No, actually, because first you got to have the cancer to get that 98% positive, and so few people have the cancer in the first place that actually becomes very rare. All right, last question here says, given that a person gets a positive result, what is the probability they actually have cancer? Okay, given, conditional, I say that word given. Okay, so the question actually says, what is the probability they have cancer? So what is the probability they have cancer? Now, if that's all it said, I would say 1 out of 2,000, 0.0005. But it says given that they have a positive result. Okay, so now I got a conditional question. You have a positive result. Should you be concerned that you actually have this cancer? All right, denominator is the condition positive result. Now, the good news is we just figured that out. 0.050465. Why waste time doing it again? We already figured out the probability of a positive result is I have cancer and I get a positive, or I don't have cancer and I get a positive. 2 scenarios, both leading to a positive result. That's my denominator. Numerator is both cancer and positive. Well, that's a very specific branch. Cancer, 0.0005, and you have a positive result, 0.98. So that numerator is 0.0005 times 0.98. That numerator is 0.00049, if you don't believe me. But then I'm going to divide that by the 0.050465. Try to use as many decimals as I can to be nice and exact here. And the probability is 0.0097. Now think about that for a second. If you get a positive result, there is under a 1% chance, 0.97% chance you actually have cancer. And you might say, well, wait a minute. If I have a positive result, shouldn't that tell me I have the cancer? No, because first, so few people have this cancer to begin with. So if you get a positive result, you shouldn't be too concerned at first. And the other thing is, the biggest branch, I know the branches all look equal, but if you're going to put some leaves or some fruit on these branches, this branch right here is the heaviest branch. It really is. Because it's the one where you get a lot of positives. You would say, well, 5% is not a lot, but 5% of the overwhelmingly large amount of people that don't have the cancer is what allows that branch to be kind of weighing a lot. First off, it weighs a lot more than this branch. You can't just look at the 98 and the 5. You got to look at the fact that where those branches stem from, cancer is very unlikely to begin with. So that's why if you get a positive result, most doctors will say, hey, let's do some more tests. Let's do some secondary tests to kind of see what's going on here. It might alarm doctors to give you that second test. But again, you got to understand the math here. Conditions and formulas and all this stuff works real nice here. So this is pretty cool. All right, hope this made sense. Hope you enjoyed it. Hope it helps you.